Now starting. All attendees are in listen-only mode.
Sorry, I was in muted and I started talking, but I think I'm set now. So, good morning, everyone. For those that you don't know me, I am Woody Cash, SCTE Golden Gate Chapter Content Knowledge Officer. Today's presentation is passive and tap performance considerations in FDX and ESD environments. When we think of FDX and ESD, we often think about nodes, AMPs, DOCSIS 3.1, 4.0, and so forth. So we get kind of tied up in the high tech end of that. But what we tend to forget is all this has to work through the passive network. So one should not just forget about the passive network when it comes to these advanced technologies. And today we have Neil Tang. Neil will be our presenter. Neil is president of Antronics. Neil has many years of experience with developing products for the broadband, broadcasting, and satellite industry. So Neil explained to us why we need to think about passives and taps when we think about this wonderful technology that we are starting to embark on. Before we get in the presentation, I wanted to take a couple of minutes to talk about benefits of SCT membership and online resources. So for Golden Gate members, we actually pay people to do certifications. So not only can you build your credentials, you can also get a little cash with that. So there's some advantage of that. You're going to learn your craft better. You're going to understand the technology and lots of changes that take place all the time. So it is really helpful if you go through these courses and if you sort of prove your learning by getting certified. So check out on our website our certification incentive plan. There's if you calculated all the certifications, it would actually add up into the thousands. Also like to just say for the SCTE, there's a vast catalog of courses. So I was going through there looking through all the courses. So we go from everything to like fiber installer all the way up through CCNA, our Cisco network associate. So take a look at that. Sometimes your employer may actually pay for some of those courses and or provide reimbursement if you pass. So check that out as well. I'd like to also say Golden Gate Chapter is a YouTube channel. So we have escaped the dark ages and we're actually on YouTube now. So you can see some past webinars there. Also, you can see interviews of our Broadband Founders Club inductees. And we started a new series, which is getting to know your board of directors. So we have the president, Don Simmons, on there. And I plan on adding about one a month. So we have one scheduled for August. So you'll see a new one there. So please check it out and give you a chance to actually get to know the people that are behind what you see here. So in addition, we are in the nomination and election process for our board of directors. Nomination period just ended. Might be able to take in some late candidates if you haven't nominated somebody already. But if you do want to nominate somebody, get those in right away. So on September 1st, the actual election opens. So that will be available to all members to select who they would like to see serve on the board of directors. So upcoming webinars, we have a few scheduled for the remainder of the year. So on 9/9, we have DOCSIS Showdown, a key difference between DOCSIS 3.1 and DOCSIS 4.0 with Brady Volt. On October 7th, we have the nuts and bolts of FDX with Frank Eichenlaub. of Comcast. And 11.4, we have Powering Critical Infrastructure with Intersys. In December, we have our Fall Training Summit. So we have some, we haven't got all the details on that, so more details to come, but it usually takes place starting the first Tuesday of December. So don't let your calendar fill up for that week, because we're going to have some outstanding presentations, and they'll probably go into 2 weeks, since we've actually brought on the Florida chapter is also involved in our training summit. So we do plan to have 6 days of training, and again, we're working on the topics, and we'll get the details out to you as soon as possible. Just a reminder, in the chat, in the questions box, put any questions you might have as we go through the presentation. I will interrupt Neil, and if you have a question on a specific slide, or as he goes through the slide. We also have a couple of poll questions, so I will be putting those out about the middle of the presentation, and Neil will also prompt me on that. So with that, I'm going to turn it over to Neil. So again, thank you, Neil, for taking time today to do this presentation.
Thank you, Woody. Thanks for giving me the opportunity to have a presentation to the Golden Gate chapter here at SCTE. I think education and for the whole community is great, and this is a topic close to my heart. So how passives and taps and line passes affect the RF performance as we move into the next generation architecture. I'm going to go through a little agenda we have here. First, we're going to talk a little bit about the current needs in the cable industry for bandwidth. Some of the solutions that we have is for DOCSIS 4.0, which is the FDX, full duplex DOCSIS, and extended spectrum DOCSIS, ESD, that we're going to talk about today. And as Woody mentioned, all these signals go through the passives in the network. Much of the industry is talking about the smart amplifiers and actives and remote PHY nodes, but the passives that are in the network need to support this architecture. And there's a lot of different parameters within the passives that affect DOCSIS 4.0. So we're going to talk about a little bit of these parameters within the passives. And we're going to talk about some other considerations that will affect DOCSIS 4.0 and tap plugin conditioning and how that will improve your network performance. So the largest asset in the cable network for MSOs is the coaxial cable. In the United States, penetration is over 88%, and it is desired to use the existing infrastructure within the cable plant with least disruption. So people are trying to go fiber deeper, but they're using the coaxial plant for the last leg in the home. So as we try to expand our bandwidth, the historical way of doing things has been doing node splitting. Node splits provide additional bandwidth to the nodes into the network, but there are some limitations. Head-end space is limited. As you node split, there's a limited head-end space. Power and cooling is limited. And also, you can also increase the upstream. This is a popular method as people move from the 5 to 42 megahertz subsplit upstream. They're going to mid-split or high split. So you're increasing the upstream bandwidth. So you could have 102% increase as you go from the 42 megahertz upstream band to a mid-split band of 85 megahertz. As you increase further to 204, 5 megahertz to 204 megahertz high split, you have an upstream increase of 385% increase in bandwidth. So that's great. You can increase your upstream, but in today's network, you can see, as you can see in the subsplit here, you have the upstream 5 to 42, and your downstream band is 54 to 1.2 gigahertz. This is what we call FDD. It's frequency division duplex. So each frequency has a specific upstream or downstream signal. So 5 to 42 is the upstream, 54 to 1.2 gigahertz is the downstream, the subsplit. As we go to mid-split, as you can see, the upstream is increased. You can go to 5 to 85 and 104 to 1.2 gigahertz. Same thing with high split. You increase the upstream, you have more bandwidth, but as you increase the upstream spectrum, you're actually taking away the downstream because your network is limited to 1.2 in this example. So no matter what, you have to put all your upstreams and downstreams in your 1.2 gigahertz network. So as you take away from the upstream, you could see you're removing and having a smaller downstream path for bandwidth. So there are two main solutions for DOCSIS 4.0. So DOCSIS 4.0 is helping us solve this bandwidth constraint. One of the solutions within DOCSIS 4.0 is called extended spectrum DOCSIS. And that's pretty much using the same frequency division duplex, FDD, but extending the frequency band from 1.2 out to about 1.8 gigahertz. It's actually 1794 megahertz. So as you increase that bandwidth, you are increasing that downstream. So this top chart here is your high split from before. But we have things here called the high split. There's other frequency bands. Now, if you go even higher in upstream, you can go 5 to 396. There's various different types of upstream bandwidths that can be used for extended spectrum going out to 1.8 gigahertz. This is what they call ultra high split. Anything above high split, they're calling ultra high split. So you can go even up to 684 megahertz upstream, and you start your downstream at 834 megahertz. So these are different network architectures where you can design your extended spectrum with a fixed crossover, so you have your upstream and downstream at different frequencies, and increasing your capacity for upstream and maintaining your downstream large bandwidth that you need if you extend the frequency out to 1.8. The other type of solution is full duplex DOCSIS. This uses a different type of architecture. This is unique where you're actually using the same frequency to transmit upstream and downstream together. So you're still using 1.2 in this case, the upstream bandwidth up to the bandwidth up to 1.2 gigahertz, but within the certain band, 108 to 684 megahertz, as you can see, this band has both upstream and downstream capacity. Using DOCSIS 4.0, both of these scenarios, you can actually have 10 gigabits of downstream, 6 gigabits of upstream, and this is about 10 to 50 times more bandwidth than what we have in your standard subsplit architecture that we have now. So we're going to go into more detail of DOCSIS 4.0 and show how this works in the network. So extended spectrum DOCSIS from the previous slide, that is using the standard frequency division duplex that we've been all used to, having a fixed upstream and fixed downstream, but you're extending the bandwidth out to 1794 megahertz, and people round that to 1.8 gigahertz. So in this scenario, though, the passives must be upgraded to 1.8 gigahertz as well. Not just the actives, but passives. In the full duplex DOCSIS scenario, you have simultaneous upstream and downstream on the same frequency. So the passives are not required if you're going to be using 1.2 gigahertz products, because you can use full duplex DOCSIS in both bands. So how does full duplex DOCSIS work, FDX? So you have upstream and downstream together, and as you can see in the 108 to 684 megahertz band, you have upstream and downstream transmission at the same frequency. This does require simultaneous upstream and downstream. There's no diplex filters, so there's no crossover band to separate the upstream and downstream bands. And the upstream and downstream can be scaled dynamically for ultimate flexibility. So as you have different areas, different segments of your node that requires more downstream, FDX can configure that to more downstream. You configure that more upstream if needed. So this can be dynamically scaled based on needs. To understand the impact of extended spectrum DOCSIS and full duplex DOCSIS, you kind of need to understand a little bit about the RF parameters in the passive. So we're going to go through some of the hardline passes in a network. Here's a typical network infrastructure. You have your power supply that is going to be inserting your AC into your network through a power inserter. You have line splitters that split your signal. So it splits both AC and RF down the line. You also have line directional couplers. These are unequal splits. So a directional coupler can actually have lower loss in the through leg and more loss on the coupled leg. So in this case, it is connected to an access point for a directional coupler to power an access point. You typically have cascades of taps, and taps are branching off the main signal to each individual home. So every F port here is connected to a home, and it taps off the signal into the home. And we're going to go into much more detail on taps and the performance and how that works. You also have drop power taps, and either called drop power taps or F port power taps, where you can have an access point connected to an F port, and that F port is actually powering the access point as opposed to the hardline cable in this line directional coupler example. And as we have signals going down a coaxial line, different frequencies attenuate more. So higher frequencies attenuate on a coax, have more attenuation down a coax. So as a signal travels down a length of coax, higher frequencies are attenuated more. So an equalizer is, and in this case, an inline equalizer that's hardline in the network, actually has an upward slope. So when you add the two together, the frequency response of the equalizer balances the loss that is in the cable slope on the network. So you have a flat response after the equalizer. So these are some of the main components in here. And as we're talking about taps, some of the parameters affecting extended spectrum and FDX, the main performance parameter is insertion loss. So what is insertion loss? You have the power going into a tap and the power coming out of a tap. Ideally, you would want no loss going through the tap, so power in is equal to power out. But there is some insertion loss on all products. So when the insertion loss is actually the power in minus the power out. So if I have a signal level of 40 dBmV going in, and if coming out is 39 dBmV, I have an insertion loss of 1 dB. That means 1 dB is actually lost in the tap of insertion loss. You want insertion loss as low as possible to have minimal loss through the tap. Another parameter is return loss. And we'll go into how this affects ESD and FDX and these RF parameters in later slides. So cable to plants has a 75 ohm system impedance. So in an ideal system, if the tap is ideally 75 ohms, 100% throughout, power in is equal to power out, no loss. Everything goes right through in a magical world where there's no loss at all. But that is not the case. It's not ideally 75 ohms. There's always some reflection. So return loss is a measure of the signal coming in and what is actually reflected out. So if this is not a perfect 75 ohms at this barrier when it interfaces with the tap, that signal goes in and a small portion of that signal is actually reflected due to the non-perfect 75 ohms of any interconnect. So the return loss is actually a measure of the power in minus the reflected power.
On that slide, I have a question for the audience, if I may. So audience, if you pay attention to this. So is a higher return loss a more desirable number, or lower return loss?
So yes, higher return loss is a better number. So it means less reflection. So for example, if I have a 20 dB return loss, you're actually transmitting 99% of your power through the tap. So the tap has a 20 dB return loss, 99% goes through, and 1% is actually being reflected back. So the higher numbers, the better, lower numbers, worse. If you have a 5 dB return loss, actually 68% goes through the tap, but 31% is actually being reflected back up reflected back out to the output of the node or the amplifier of the tap. So definitely the higher return loss, the better. But every interconnect is non-ideal and has some degree of reflection. So you don't have a perfect return loss on everything. So every connectorization, every interconnect needs to be properly spliced and checked. And even water migration can affect the return loss on every interconnect. So make sure everything is actually sealed well and prepped correctly. So for example, we have a return loss, a 20 dB return loss in tap. And if I have an input signal level of 35 dBmV going into the tap, you're having a reflected output power. So it comes in, some of it's been reflected, and the reflected power is actually 35 minus 20 is 15 dBmV signal level is actually being reflected going backwards from the tap due to the return loss. And that number gets larger and larger as the return loss gets smaller and lower. So if you get a lower return loss, let's say you have a 5 dB return loss, if your power input is 35 dBmV, your reflected power is 30 dBmV going back up the cable. So what is a tap? So a tap is actually here to tap off the main line to each of the F connectors that goes down to a drop to a home. Typically, taps come in 2-port taps, there's 2 F connectors, 4-port taps, 4 F connectors, and 8-port taps. And they come in various dB values here. So as you can see, this is as a number 23 on here, 24. This is the actual loss between the input and the F port. So it's the loss going through the tap to the F connector. Not the insertion loss, but through the tap to the tap port. So here's a block diagram of a tap. And you can see the tap is actually has AC going through what we call a choke, a big filter in here that allows AC to go from input to output. So all your devices on your hard line is being powered through the AC voltage, 60 or 90 volts AC on your hard line. That goes through the tap as well. The blue lines is the RF path. So the RF path has a directional coupler. This is the symbol for a directional coupler. It goes in, out, and a tap. So the signal goes through from in to out. So the lower loss port is going through the tap. As you can see, the low loss goes through the tap, so with lower insertion loss. Then the tap port has higher loss. And a tap can control the loss through the tap by different directional coupler value. So whatever the tap value here, I can make this a higher loss or lower loss. But keep in mind, whatever I'm coming out in, whatever's going into this port, you're splitting it to the output ports. So you can't create power. You know, if I put 90% of the power through the output, you get 10% of the power here. But I can also make it 50-50. But that means I'm having more loss at the output, but I have 50% power on each of the ports. So this is configurable based on the design, and that determines the dB value of the tap. And after this directional coupler here, as you can see in the block diagram, this is a splitter. So that signal is split to the 2 ports. This is a 2-port tap in the F connectors. So this is an equal power divider. So it comes in and splits it out equally. So each of the F ports have the same signal level, signal power going out of the F ports.
So I have a question on this slide, Neil. So can you tell the audience what would happen if that RF choke was missing for some reason?
So if the RF choke is missing or there is no RF choke, then there is no AC going down through the tap. So RF may still be there. There's the capacitor here. RF goes through the tap. You can have RF. But if that choke is missing or not there, you cannot connect an AC device. AC is not going to be going through the tap into output.
What if there was just an AC pass-through with no RF choke? What would happen to the RF?
The RF would still be there on the signal. So if there's no AC choke, the RF would be still there. I mean, if it's actually cut out, accidentally cut out, this is actually tuned to the circuitry here. So your RF could be affected if it was damaged and cut out of the board.
Okay, so if it was passing through RF through that AC circuit, you end up with two or a split RF signal that's recombined, right? So you would have some distortion in the RF system. Okay.
Correct. So in a tap, you know, the goal, why you have taps, the goal is for the system design to have the same signal level to go to each home of the subscriber in the network, irregardless of the distance from the amp or the node. So how do we do that in the current network is the taps will have different dB values. And that means there are different losses to the tap ports for each of the taps. So they attenuate the signal differently as they travel down the length of coax. So each signal is consistent at every home. Let me illustrate that a little bit. So are there different tap values? And for this purpose, we're going to assume flat loss across the frequency on coax, which is not the case, but for just explaining why you need different values of taps. So for example, if you have a 40 dBm signal level output of an amplifier, as you're traveling down, you want a goal of, let's say, plus 12 dBm output at each home throughout the whole cascade. As you're going down the signal through the coax, let's say there's 5 dB of loss on the coax here. At the input of the tap, you have 35 dBm in the tap. So to be able, if you have 35 dBm on the input of a tap, and you want a 12 dBm signal level each home, you want to have a 23 value tap. That is 23 dB loss between the input and the F ports. So that's, therefore, the signal levels going to the home here is going to be 12 dBm. As we continue that signal down the line, as we mentioned, going through the tap, you want low insertion loss. You're going to go through a lengthened coax, and let's say you have a 32 dBm signal at the input of the second tap. But I still want 12 dBm at each home over here. So if you put a 20 tap there, 32 minus 20 is 12 dBm, and that becomes 12 dBm at the tap. So as you can see, as we go down the cascade, 26 dBm signal level at the input of this tap. If I want 12 dBm, you're going to put a 14 tap. As we proceed down further, 20 dBmV, if I want a 12 dBmV at the home, you'll need an 8-value tap. But as the signal gets too low, you're not going to be able to use a passive to get the signal to 12 dBmV. So as the signal gets lower, you're going to need another amplifier to boost the signal. So this is why you can see there are different tap values, 23, 20, 14, and 8 in this example, in the cascade to provide different losses so that each home, no matter where you are or the distance you are from the amplifier or node, you're going to have a consistent, in this example, 12 dBmV output at each home. So multi-taps have various RF parameters. We mentioned before the insertion loss. That's the signal going from in to the output of the tap. This is a typical insertion loss plot. And you can see insertion loss varies with frequency. As you go up in frequency, loss is typically higher. Lower in frequency, loss is lower. So going down here, 0 is ideal. That means no loss. This is the amount of loss going through the tap, 5 dB, 4 dB, 3 dB. So as you can see at 1.2 gigahertz, this is about 1.8 dB insertion loss, whereas where you're down in 100 megahertz, it could be about 0.8 dB insertion loss. So higher frequencies typically have a higher insertion loss in passive parts. And when we mentioned before on a 23 dB tap, going in through the F port, this is called tap loss. So the loss between the input of the tap and the F connector, and that determines your tap value. And there's 23 across the board and frequency response I could see here. There's also parameters called isolation. So as a signal is going upstream on a cascade from the output to the input, so there's homes connected to the output of the tap that are connected to taps further downstream. So that they have cable modems transmitting upstream, going through the tap, going back to the upstream, into the amplifier for upstream, going to the head end. And you do not want the upstream signals of homes, those cable modem homes, affecting this tap. So you want high isolation. So if any signal level going through the output will have some small leakage going into the tap. And we call this isolation from out to tap. And we want that to be high. That means we want good isolation. We don't want any signals from downstream cable modems to affect any cable modems connected to this tap. So the higher the isolation, the better to prevent that upstream interference.
If I may, Neil, I'd just like to emphasize that the isolation becomes ever more important as the bandwidth of the return widens. When you have like 500 megahertz of return bandwidth, if you have poor isolation, it will actually interfere with the other customers on those same tap ports. So making sure you have the right cable simulator or attenuator in the tap becomes very important.
Yes. And as you can see, the isolation is not a uniform straight line. It varies with frequency. So you should check the vendor's specifications. They typically spec the worst case. So, this tap may be specified at 30 dB worst case, where everything's at least 30 dB. And typically it's better than that. And there's a curve associated with isolation. Same thing with tap-to-tap isolation. Now, this top image was out to tap. These are cable modems downstream. You don't want that to affect the cable modems connected to this current tap. There's also tap-to-tap isolation. You don't want a cable modem that's connected to port 2 on a tap to affect the cable modem on port 3 of the tap. So you still want high isolation between the F ports of the tap. So this is called tap-to-tap isolation when you look at specifications on an RF tap.
Yes, and
And also,
I apologize. I should have mentioned that, it was the tap-to-tap isolation I was referring to. Obviously, the isolation tap output is just a product of the tap value.
yes. And so the isolation from tap to tap is actually higher. It also has a curve as well, and you want it to be as you have different tap values, it affects your tap to tap isolation as well, and you want the higher tap to tap isolation to make sure each cable modem doesn't interfere with each other. Return loss. So return loss is what we mentioned before. Some of the signal level coming in and is reflected. I mentioned before 20 dB return loss. Here's about 99% of the signal levels transmitted. Return loss is not continuous with frequency as well. Each frequency has a different return loss. And specifications are usually worst case return loss on specs. So this would be a typical plot out to 1.2, and the higher number here is better for return loss. Same thing with output return loss. There's signals going upstream on the output of a tap, and signals could be reflected in that direction as well. Likewise, there's a tap return loss. Each of the F ports have a return loss as well, and that's on specifications as well. So the cable modem that's connected to an F port has an upstream signal cable from the cable modem, hits the tap port. Some of it's going to be reflected down due to the tap port return loss. So how does, extended spectrum? Most people know how extended spectrum works because that is exactly the way we're doing the plant now. We're just extending the frequency out to 1.8. But full duplex is a little bit different. It's more complicated and has certain technologies in there to allow upstream and downstream transmission on the same frequency band. So we're going to talk about a little bit how full duplex works here. So you typically have a CMTS fiber link connected to a node and a cascade of taps. And the taps F ports are connected to individual homes. So one of those homes, you'll have a cable modem. And one of the key things about the FDX, how it works, is what they're called an echo cancellation device inside the cable modem. So this feature within the cable modem is a technology that actually allows the echo, the return loss, the signal that's transmitted reflected back, to be canceled. It's called an echo canceller. How does that work? So if I'm a cable modem, I know the signal I'm transmitting. So what I'm going to do is I'm going to be transmitting my signal upstream. If I know what I'm transmitting upstream, I can do a negative of that, 180 degrees out of phase. I know that I could put that signal into the echo canceller on one side of the echo canceller. As this signal goes up, my upstream signal goes up, I'm going to hit the tap. I mentioned the return loss is not perfect, so something's going to be reflected back. That same upstream signal will be reflected back going down the downstream with the proper downstream that you're trying to detect. This is your receive signal from the node. So that's going to be a downstream coming here. So it's going to be added together. So down the coax, you're going to have the downstream signal from your node. That's the desired signal. And this reflected upstream from your, I'm going to say poor return loss. Every tap has a return loss that will have some reflected upstream. So reflected upstream, they're going to be added together. But the echo canceller will cancel the upstream signal, so you're only left with the downstream. That's the magic behind the echo canceller. It's done in software, and you have an echo canceller in the cable modem at the home where it allows it to transmit upstream and downstream in the same frequency to cancel this echo. You also have this echo canceller in the node as well. So those are the two locations where we have the echo cancellation. It cancels through the return loss coming back, and you could actually decipher the desired downstream signal only once you cancel the upstream signal. So here's a scenario for full duplex DOCSIS, and you have a high tap value. So this tap is very close to the node, and this node is transmitting at a very high output level. You know, current nodes have TCPs of greater than plus 70 dBmV. So in this scenario, you want, there is going to be an echo when you hit the input return loss for the tap. So this has an echo because of the high signal level, the reflection's higher. So this has a higher echo due to the high value taps. So for FDX, it's pretty important on high tap values. So on high tap values, you do want to have very good return loss. So high input return loss to prevent that echo, especially on taps close to the node, because the signal level is higher, that means the reflection is higher. So that is one key parameter to support FDX is good input return loss, specifically in high value taps. Another key parameter for FDX is for low value taps. In low value taps, you have, for example, a cable modem transmitting at plus 40 dBmV going from the home up. You have the desired signal from the node, from the head end, going to the home. So the desired signal is plus 10 dBmV. So you're transmitting at plus 40, you're receiving your downstream signal from the head end, from the node at plus 10 dBmV. Some of this 40 dBmV is going to be reflected once you hit the F port. In the imperfect return loss, we'll have some reflection, but there's an echo canceller. So we talked about that. It's going to cancel this echo, so you can just receive this lower level plus 10 dBmV signal from the head end. So you're able to receive that signal fairly well. The problem would be if I have an adjacent home on a tap. The adjacent home could be transmitting at that same plus 40 dBmV, but due to the tap-to-tap isolation spec, let's say I have a 20 dB isolation, you are actually having a signal level of 20 dBmV from the adjacent home going down to this home. This 20 dBmV is higher than your actual receive signal coming down and will cause this home to be interfered by the cable modem in this home, because the echo canceller can't cancel an adjacent home's cable modem. I can only cancel my own signal. So it's pretty important to have high isolation taps, especially low value taps typically have lower isolation. So in low value taps, you want to make sure you have a high enough isolation to prevent this from happening. So good echo cancellation is good at canceling self-interference. So echo canceller can cancel myself, this reflection from this blue line, but it can't cancel adjacent or other cable modems, for example, the red signal. So how do we solve this problem? We create what we call interference groups. So because these two homes can be potentially interfered, we make sure they don't transmit and receive at the same time. So one would transmit at a certain time slot, and another would transmit and receive at a different time slot. So I would assign port home 1 to interference group 1, home 2 to interference group 2. So therefore, when I'm transmitting downstream, all interference group 1 and 2 will not be transmitted at the same time. so they will not be interfering with each other. And that is a way to prevent the isolation issues between tap ports. So the full system, in this case, the CMTS view, is still operating full duplex, but each cable modem, the data for each cable modem in an interference group, is dynamically assigned a resource block allocation, and that is a simplex operation. So, each interference group is assigned a certain time slot, a resource block to transmit and receive at that time period. I think now's a good time to put some of those questions on, Woody, for the audience.
Okay, Neil, just give me a second. I'm not very proficient at this, but we'll get this up here. So let's see. I hope you guys can see that. When do you intend on deploying FDX or 1.8 gig in your network? So the options are: I'm deploying now, within the year, in 3 to 5 years, no plans to deploy, or I have no plans, but not, or I have plans but not sure when. So we'll give the audience a couple minutes to start working on that. So we got about 6% voted so far, so we'll give it just another minute. I'm going to go on mute. We'll give it just a second here.
Okay.
I've heard of some people actually doing some amp replacements and putting FDX amps in. In fact, I talked to a couple of folks at Comcast that deal with the FDX amps, and they were telling me how many were deployed. So they're getting out there, but I know they're probably still a long ways from actually deploying the FDX technology. In fact, I'm not sure, Neil, but have modems been released for that technology yet? Or are they still just in the prototype stage?
I believe they are doing some trials. I'm not sure if they're actually deployed out in the modems yet. I believe there are some, though, in terms of trials, but I don't know if it's commercially available yet.
And I think CMTSs have been available for a bit, or at least have been tested and approved, so should be coming along soon.
Yeah.
So I think everybody's hasn't got their first cup of coffee down this morning. We've only got 23% voted, but it's kind of stagnant now. So we'll go ahead and close the poll. I'll display the results. So it looks like 43% said they are deploying now, and 29% in a year, and the other answer was their plans but not sure when. That was 29%. So looks like a fair amount of people are getting ready to experience FDX or ESDX.
Right.
Okay, we will go to you want to do the other question?
Maybe we can do that a little later. We'll
okay.
Continue further. Okay.
Let me hide this. There we go. We're back to your normal screen.
Sure. Great. Okay. All right. So we have 1.2 gigahertz taps and passives. So for DOCSIS 4.0, full duplex DOCSIS FDX works fine to 1.2. As I mentioned, if you decide to go to extended spectrum, passives need to be upgraded to at least 1.8 gigahertz. Using extended spectrum at the 1.8, the taps need to be upgraded to a 1.8 or 2 gig tap and passive. There are some other considerations too when you are using extended spectrum and FDX. So these nodes for DOCSIS 4.0 are remote PHY devices. And they're like little mini computers, which require continuous AC power in those amplifiers. So any type of AC power interruption in the hard line may cause the RPD, remote PHY device, either it's a node, to reboot. And some of these reboot times can be as long as 10, 15 minutes. So let's say a technician goes to a tap or a line passive and they pull the faceplate off, and if there's any interruption in AC, that whole node will be down, may be down, if it's interruption for AC, may be down for 10 to 15 minutes while that RPD reboots. So you want to make sure that there is continuity of AC, and what we have is taps. This is an inside of an Intronics tap. This is what we have, a make before break. This is a bypass. So as you insert a faceplate into this housing, these two white actuators compress down, and this is a shorting RF AC bar that connects the input to the output. So as you remove the faceplate, the signal is still connected from input to output. And that's what they call a make before break bypass in the housing. So as you remove the faceplate, it makes connection to the input to the output to ensure that there's no interruption for AC and RF when you remove the faceplate. So this ensures that there's continuous, AC and RF downstream. So there's no RPD reboots. Other products, line passes. So typically line passes, to keep in mind, do not have a make before break. These are 3-port devices or 4-port devices. So they could be a power inserter, directional coupler, 2-way splitter, and it could be a 4-port device, which is a 3-way splitter. So you have a 1 input, 3 outputs. So it could be a 4-port device. So typical line passes have a housing where if you remove the faceplate, you will have interruption of AC and RF. So if you pull the faceplate off, the inputs and outputs are not connected. There is more difficulty of putting a bypass into a housing of a line passive because there are 4 ports. Putting a bypass to each of the port is more difficult, and the problem is some of these DCs have a 16 dB directional coupler. So if it's a 16 dB directional coupler and you pull the faceplate off and it bypasses and shorts it, your signal level is 16 dB higher during the moment period of time where you pull the faceplate off, that it could overdrive the upstream node. So there is no bypass in line passes. So this has a removable faceplate. The advantage is a quick faceplate replacement if I need to remove the faceplate. The additional advantage is that when I pull the faceplate, there's AC interruption, and it could reboot the RPD node. There's an alternate line passive where you could have a line passive where you have the printed circuit board in the housing. So if the printed circuit board is in the housing, the advantage is when you remove the cover, you could remove the cover to configure the AC and remove the fuses to have AC going on whatever ports you need. There's no AC RF interruption. But the disadvantage is during failure, there's a lightning strike, devices down, that you need to resplice because this is part of the housing. We do have product here that has some features here that allows this to be replaced in the field. These are captive screws. There's these little handles here. You could pull this faceplate out and you could press fit another faceplate in, so you don't really have to resplice in this product. But you got to keep in mind If you do have two different versions, certain versions with faceplates in the cover or in the housing, as you remove those faceplates, you could have AC interruption and reboot your RPD nodes.
So Neil, this is the one in the housing is you can still slip it out. Looks like it has some pull tabs
this
on it.
one here, so these are 6 captive screws.
Okay.
So you can remove the screws, and these 2 plastic handles you pull. It's a press fit.
Okay.
And you can get a new line passage, take it out of that housing, and press fit it into here, and screw the captive screws, and screws the captive, so you screw them back into the housing. So this way, when you remove the faceplate, you're not interrupting AC, and you're not pulling down the whole node for 10 to 15 minutes during RPD reboot.
Yeah, as a technician, I've always experienced those where you drop the screw in a bush or something. So, are you by any chance providing extra screws for those situations?
It doesn't come with extra screws, but the screws are captive. So as you unscrew them upside down, because they're upside down,
they don't fall out
in the board. Yeah. So.
Oh, okay, perfect.
Yeah. So they are captive. So yeah, they will. You don't want them falling down because you won't be able to find them. And as you insert a new one, they are captive. So as you hold that board upside down, these screws are captive to the printed circuit board, so they won't fall out.
Perfect.
Unless you really try to pull them out. I'm sure you could get them out if you wanted to, but yep. Those considerations are both for extended spectrum and FDX, because those have RPD nodes associated with 1.8 gig nodes and FDX nodes. For equalization, there's a few ways to equalize signals in a cascade. So as a signal travels down a cascade, the cable slope has higher attenuation at higher frequency. So as you travel down the signal level, you will have a slope that increases as it goes down the cable line. So there's devices called inline equalizers. This is the frequency response of an inline equalizer in the downstream. It's supposed to equalize the downstream. It has a kind of this upward slope because cable has this downward slope. And as you add the two together, you get a flat response. So you would put a specific equalizer to equalize any type of downward slope, so you get a flat response at the home. There's 2 different types of equalizers, inline equalizer, and you splice this inline in a hardline plant. You have a diplex version or a full bandwidth version. And in this case, I showed a 5-to-42, a subsplit diplex version. So you have minimal loss from 5 to 42, and then you have your equalization, 8 dB equalization from 54 up to 1.2 gigahertz in this diplex version. There's also other versions for full bandwidth inline equalizers. That means that has this frequency response with no diplex going all the way down to 5 megahertz. So in FDX, you don't want any diplexers. We mentioned that you can transmit and receive at various frequencies. So typically FDX systems use full bandwidth equalizers across the whole spectrum, and you're not fixed with this fixed diplex, because if you change diplexers down the road, if you change your upstream, you'll need to go back to this device. You can move the faceplate and pop in another one to move the diplexed version to whatever bandwidth. You're going from a subsplit, a mid-split to a high split, different versions of a diplex version of an inline equalizer.
So just to recap, if you have duplex or a diplex version, which many of us did back in the day, it's just a faceplate swap. if we want to upgrade those to the full bandwidth.
Correct. They have the same footprint, and you can pull that out from a diplex version to a full bandwidth version with no diplex filters. So yeah, we don't recommend the diplex equalizer version, especially in full duplex scenarios. The other type of conditioning and equalization you could do is tap conditioning. So this is a basic block diagram of a tap. You have the input, the output. This is the AC goes through this, what we call inductor, a choke, and the RF goes down through this directional coupler to a two-way splitter. So this is a two-port tap. And we have a plug-in conditioner. So this is a device that you can change the filter of this conditioner that is in between your directional coupler and your splitter. So what that does is, because this conditioning is after the directional coupler, it doesn't have an impact on insertion loss. So whatever insertion loss you have through here stays the same regardless of what plug-in conditioner you decide to use. Taps are typically shipped with a jumper pre-installed. So it's as if no conditioning is there, but you can remove the jumper, purchase different types of conditioning filters to put in here depending on your scenario, which we'll go into in a few slides. This conditioner only impacts the tap ports. So if I put a cable equalizer here, the tap ports will be equalized, not the through line. And as depicted, all tap ports are conditioned. You cannot condition an individual port with this plug-in conditioner. So whatever I put here is split into two here, so it affects both tap ports in this example of a two-way tap, two-port tap.
And Neil, while you have this slide up, is it okay if I say something about it? Just to try to clean up what I was saying earlier. It's the plug-in conditioner that actually has some impact on your port-to-port isolation. So what I was trying to let the techs know is that if the plug conditioner was missing, that could interfere with our customers' modems could interfere with each other in some cases.
Okay, that's what you mentioned. Yes, if this plugin, when you mentioned this choke was missing, no. So if this plugin is missing, yes, you definitely will not get any signals in the tap port. And if you forget to plug this, if you pull it out, it will also affect your insertion loss, because keep in mind your RF, this is a 3-port device, this directional coupler. So you want a good 75 ohms on each of the ports. So this is connected to the network, which is 75 ohms. The output's connected to your network, 75 ohms. But if I forget to put this plug-in in, this is open-ended. So that's it will create reflection if I forget to put this plug-in in, and will affect your through line as well.
Or let's just say there was the design called for a plug-in conditioner and it was missing.
Yep.
Your port, and it just had a jumper in there, your port-to-port isolation might be very poor.
Yes. So here's the different types of tap plug-in conditioning. The frequency response, the filter shape, is shown here. So everything is shipped with a jumper as a bypass, shipped standard with a tap. You have what we call a cable equalizer, which have an upward slope. So these cable equalizers, we'll go into a little bit of detail in a few slides on when and how we use these. They would have a certain dB value of equalization. And that would be your loss at low frequency. So if it's a 10 dB cable equalizer, you would have 10 dB insertion loss in the low frequency, and minimal insertion loss in the high frequency. And these are typically used at low value taps at the end of the cascade. A cable simulator is, as the name states, simulates cable response. So cable response have a downward slope. Higher frequency has more loss, and you could get different types of cable simulators at different dB values, depending on how much cable simulation you need. And these are typically used at higher value taps, close to node ramp. There's also diplex versions. So you have flat loss in the upstream, flat loss, minimal loss in the downstream. So it's a return path attenuation. We're attenuating the upstream. Now these are diplex plugins that go into the tap. And there's also called a high tap value plugin, where it is a forward path attenuator. And flat loss, minimal loss in the upstream, and forward attenuation on the downstream. So, but these have diplex versions, and they do the similar things as the cable equalizers and cable simulators. As you can see, the cable equalizer is something like the return path attenuator, except it's flat lines. You know, it's just, so you can accomplish what you're doing, what you want to do with the cable equalizer, with a cable equalizer in place of a return path attenuator. And like vice versa, you could do what you need with a high tap filter with a cable simulator. So we don't recommend a diplex version. Those were available a long time ago, and less customers use them because we recommend using a diplex agnostic version. So in case your network is going to be upgraded from subsplit 5 to 42 to a mid split or a high split or even an ultra high split down the road, you don't have to revisit the taps and change these plugins down the road. So these diplex versions are not recommended. So in tap plugin conditioning, there's a cable simulator used in high value taps, and I'm going to use an example here, a 32 value tap. Nobody uses 32 taps anymore, but why would you use a cable simulator? Because you have 32 dB loss in the tap, this cable modem is transmitting at a very high level, and we're talking high, screaming at plus 48 dBmV, because the upstream signal needs to overcome the loss of the tap. There's 32 dB tap, so you're transmitting at a very high level. Simply changing this tap to a 23 tap, so and a cable simulator of 9 dB, that means in the high frequency band, I'll have 9 dB more loss. So I will have a 32 dB tap in the high frequency band, but in the low frequency band, I have 23. So therefore, this cable modem transmitting the upstream, I'm only seeing 23 dB of path loss through this tap. I can transmit at a more normal level and not needing a very, very high level on high value taps to overcome. So those are some of that is an example of where you would use a cable simulator in high value taps. Cable equalizers are typically used in low value taps. So as the signal travels down the coax, higher frequencies get attenuated more. And towards the end of the line, you get a frequency response with a tilt going downwards. And because the cable modem at the end of the line needs to only overcome 8 dB loss on this 8 dB tap, and cable modems travel in the low frequency band, there's less loss on coax and low frequencies. So the cable modem only needs to transmit at plus 30 dBmV at a very low signal level on low value taps. So at end of line, we also know that because of this low signal level, your carrier to noise is worse. You're transmitting a lower frequency, and ingress tends to be prominent in low value taps because any noise within the house, there's only 8 dB of loss going into the plant. So any noise here, there's only 8 dB of attenuation of that noise in the upstream going back into the plant. So a couple concerns, but if you use a cable equalizer, let's say you have a 10 dB cable equalizer here, it does two things. It actually attenuates your, because the cable equalizer has loss, 10 dB loss in the upstream, it attenuates your ingress by 10 dB, and it gets rid of that tilt, and you have more flat response, and therefore your cable modem upstream is transmitting at a proper level. So cable equalizers are used in low value taps, and cable simulators are typically used in high value taps. So if you look at a typical design, we're going to show some modems with some low output levels. How do you provide better tilt at the tap? And we can also improve signal to noise. Typically, in a plant, you can have, this is a distribution of signal cable modem transmit power, and you want to be in the sweet spot. This is the quantity of modems in that sweet spot of signal levels, but there are always some modems transmitting very high or some modems transmitting very low. And we can address those cable modems by various different types of plugins. If you condition the tap properly, here's an example before conditioning. I have a modem on your node, a cascade of taps. This is the transmit level at each tap. And so we're looking at this this is 870 megahertz, 860 megahertz signal level with a 18 to 10 dBmV tilt. So at this 24 tap, this modem is transmitting at a plus 41 dBmV. Assuming this is the cable loss between each tap, the insertion loss of each tap is down here in blue. You could see that the variation between the transmit level is, from the lowest is 30 dBmV to the highest of 41 dBmV. So there's a 11 dB variation in upstream transmit level. By just making two adjustments at the end of the line, we're going to add a cable equalizer on the 15 tap and another cable equalizer on the 8 tap, a 10 dB version. This attenuates the upstream by 10 dB and boosts the cable modem signal up by 10 dB. This boosts it up by 4 dB. You could see now that the cable modems are all transmitting in their sweeter spot, and the variation for the upstream and transmit upstream highest transmit level to the lowest transmit level varies only 4 dB in this scenario. So just a couple plugins in your whole cascade conditions the whole network for better carrier to noise, lower ingress, and having a more uniform transmit level. So the key part is you want to make sure you follow the design in the network. So you want to follow the design. This is not a tool for techs to try different plugins. Hey, does this work? No, use the plant design, whatever the design requires to use in the right plugin. You want to put the other poll question in there, Woody?
Sure, just give me a second here. And by the way, I've got some activity in my house today. So if you hear noise in the background, please forgive that. So give me a second to get the poll started here. Here we go. So, which is the preferred method for equalizing cable slope? First choice, equalizers via tap conditioning plugins, inline equalizers, or both. So I'm going to go. We'll give a few minutes. We got a few people voting, so hopefully everybody's paying attention, can participate in this poll. And the cool thing, Neil, I've got a question for you about the inline EQs. When did the full band equalizer and cable slope versions come into play? Because I don't remember those being available when I left the industry.
They were available actually very long ago, back in the 870 days, but not a lot of people were using them because they were using diplex versions. But they're more so, I think we launched ours pre-COVID timeframe, around COVID timeframe, when 2019, 2020, around that timeframe. I got to check the dates, but that's
Okay.
when they really started kicking off, and everybody started using more full bandwidth equalizers.
Is one thing we were looking at is having to go through and replace all of those and then going and equalizing these taps. So one of the options would have been we could have just actually changed the inline EQ, and that would have got us by. Not as well as going through and equalizing the taps, but certainly would have got us through.
Yeah, and different cable operators have different approach to that. As the designs for DOCSIS 4.0 gets more stringent, the power budget is tight, so any insertion loss or extra loss is not desirable. The tendency is moving more towards tap plug-in conditioning, where you would put in different conditioners in to equalize, because those conditioners don't affect your insertion loss. An inline equalizer does have some insertion loss of about a couple dB, a dB and a half to 2 dB. So putting one of those in will actually put a couple dB of insertion loss in your through line, since DOCSIS 4.0 power budget is very tight. So the recommendation is using tap plugins, but it is more cumbersome. You could tweak each tap to have the ideal signal level, but you do have to visit more taps or plug in to a few different taps to have the ideal power level and frequency response.
Okay, I'm going to close the poll now. We're actually got up to 41% voting, so people are looking at this and reading it. So hang on a second. Let's close it and let's share it. So here we go. So the answers were equalizers via tap conditioning plugins, 58%, and 25% of folks said inline equalizers, and 17% said both. So I'm going to let Neil answer that question. Neil,
Okay.
What do you think?
So there are networks, cable operators that have used both, and even though they're different networks, typically you would have one node solely tap plug-in conditioning, another node could be inline equalizers, but one cable operator may have both flavors depending on what network they're actually using. So both are valid and easy to use. Obviously, one spliced in conditioner is easier because you're only putting one device down the whole cascade, but it is more of a crude equalizer method, and you are adding insertion loss in there into your network. So,
yeah, I was to express my opinion, it's the tap conditioning that is far better, if possible, because you can really narrow that window, which is very helpful. And one amazing thing about tap conditioning is an installer service tech that goes to the tap, they pretty much know what level, transmit level and receive level, they're going to get at each tap, because it's going to be really close.
Yes. And that's where, where DOCSIS 4.0, that's where most cable operators recommend the tap conditioning. And that's a training we do separately. A lot of cable operators want us to get a little bit more detail in terms of what types of conditioning they use. And we have various different types of filters, both on 1.2 gig networks and 1.8 gig networks that properly filter and condition your signal levels depending on your scenario of each tap. So that is pretty much my presentation. Looking to open it up to any questions from the audience or anybody.
I'm not seeing any, but we'll give it a second. Does anybody have any questions for Neil? It's a really good topic. I know I find it very interesting. I know I'm not out there dealing with passives and taps anymore, but still, there's just a lot of interesting information about taps and passives, especially now that we have tap conditioning and inline conditioning. Really optimize the network for optimal performance.
Right?
I hope not everybody else is hearing the echo that I'm hearing. Any questions, anyone? Well, I again apologize for the background noise. Not only is there some construction work going inside my house, it's garbage day too. So garbage truck is outside. So I apologize for all the background noise, but I'd just like to take a moment to thank Neil. Thank you so much for providing this information and this training to us. Very helpful, and I hope everybody got a lot out of it. Hang on, I think I have a question now. Says, hey Neil, this is Kelly. Oh, great job today. So Kelly says, great job today, Neil.
Okay, thank you, Kelly.
So comments are always welcome. Questions are welcome. But I think we're done here today. So just hope everybody has a nice day. So again, for our September webinar, really exciting webinar with Brady Volp, one of the most enthusiastic people in the industry that I know. So great presenter, a great topic. He's going to highlight the difference between 3.1 and 4.0, which there's some amazing things that 3.1 people don't even know because they haven't even utilized that technology in its fullest. But 4.0 even does even more. So it is going to be a very informative training. So thank you again, Neil. Thank you for all the attendees, and we will call it a day. Thank you, everybody.
Thank you, everybody. Take care.
Take care.